Felix Baumgartner is famous for jumping from a height of 40 kilometers, oh my goodness, above the earth. So he fell for over 4 minutes before he was like, all right, time to open my parachute. So here's our dude Felix falling for a very long distance. And here's the earth. And at some point, I don't know, maybe a bit closer to the earth, he opened up his parachute. I'm sure his parachute looked exactly like that, like an avocado slice. But we're given a graph of his speed and time. Now just looking at this, when do you think he opened his parachute? What section? If you thought section A, B, or C, you're wrong. Sorry to do you like that, but this is a graph of his first 60 seconds, whereas we know he opened his parachute around 240 seconds. So this whole graph doesn't even show us where he opened his parachute. It will be somewhere in the future. But so what this graph does show us is his speed against time for the first 60 seconds. So it makes sense. At time 0, he had no speed, right? This is before he jumped. As time increased, his speed increased up to a certain point, right? So for the first 30 seconds, we'd say he was accelerating. His speed was increasing over time. And then in section B, something happens. And finally, in section C, he's traveling at a constant speed. And we call that his terminal velocity. So just to summarize this, we know in section A, his speed is increasing. So they are accelerating. In section C, they're traveling at a constant speed because it's a horizontal line. Constant speed. And we can actually read off that speed. That is 350 meters per second. And in section B, to go from accelerating to a constant speed, what needs to happen? So would we say they're decelerating? Or would we say they're accelerating less? Right? We could say either. So accelerating, and then he slowly stops accelerating to then transition into a constant speed. All right, so question A, looks like we've already answered that. Describe Felix's motion in sections A and C of the graph. So in A, we said accelerating as his speed was increasing as time increased, and we know acceleration is the change in speed over the change in time. So he was accelerating. In section C, on the speed time graph, we see a flat line, which indicates a constant speed. There could be a flat line at 0, which means they're stationary, but that is also a constant speed, right? It's just a speed of 0. But in this case, he's definitely not going 0 meters per second. He's going 350 meters per second. So constant speed. And because we're extra smart, we're just going to put in the speed he's going. This is, I guess, optional, because that's just describing his motion as saying things like accelerating, stationary, or constant speed. Question B, state the maximum speed reached by Felix. So from this graph, the maximum speed is we look at our curve, so this curve here, and where is the highest value on our speed axis? Well, that's actually in section C, and that would be 350 meters per second, would be his maximum speed. Now, we don't know what the graph looks like over here, because we're only given the first 60 seconds, but if we think about it, this would be his terminal velocity, which means the forces of his weight force would have balanced with the frictional force, and he won't be able to gain any more speed. So the maximum speed reached by Felix is 350 meters per second. Question C. Use the graph to calculate Felix's acceleration in the first 30 seconds. So first 30 seconds is section A again. And we know acceleration is the change in speed over the change in time. So acceleration equals, what is his change in speed in the first 30 seconds? Well, he starts at 0 and he gains a speed of 300 meters per second. So the change in speed would be 300 minus 0, which is 300. Divided by the change in time, we know it's the first 30 seconds, so it's 30 minus 0, or 30. So his acceleration would be 300 divided by 30, or 10 meters per second squared. So we've just shown our working above. 10 meters per second squared. Oh, they've already given us units. How nice. They're not usually this nice, so be on the lookout to be putting your units in. But that's very kind of them. Question D. Calculate how far he fell in the first 30 seconds. Okay. So how do we get the distance from a speed time graph? Distance from a speed time graph. So we got the acceleration from the gradient, right? Change in speed over change in time. To get the distance, we actually use the speed distance time formula. If we just rearrange for distance, we get speed times time equals distance. And see, we're multiplying here. So speed times time will give us an area under a curve. So from a speed time graph, we can get distance by getting the area underneath the graph. And in this case, we want the area for the first 30 seconds. Which, lucky for us, is a triangle. And we know the area of a triangle. So area under curve in first 30 seconds is equal to distance. So the distance traveled in the first 30 seconds, which is the area of a triangle, which is half times base times height. And the numbers we will use, half stays as half, base is 30, and height is 300. So just putting that into some proper working down here. Distance in first 30 seconds is area under curve in first 30 seconds. So I'm just being very exact in what the distance corresponds to. So distance equals half times the base times the height, which is, what is that, 4,500 meters. Don't forget your units here. So in 30 seconds, he has traveled 4.5 kilometers based off of this speed time graph, right, where he's accelerating at 10 meters per second squared for that time. Oh, they gave us the units again. Wow, this paper, they're too generous. Right, on to the final question. We're given the graph again. How kind of them, again. And we need to draw and label arrows on the diagrams. So let's just draw our diagrams here. Beautiful. to show the size and direction of the vertical forces in section A and C. The vertical forces. So let's have a think. Well, Felix assumedly has mass, so he will have a weight force. And that will be in both section A and C. Is his mass the same? Yeah, he's not like burning fuel or anything. So actually these two weight forces will be the same, so the same size, because Felix has the same mass in both section A and C. So that makes sense. What other vertical forces do we have? So what's the upward force? That would be friction, right? Or air resistance. But what would the sizes be? So in section C, he's traveling at a constant speed, which means there's no net force, right? He's not accelerating. So the force due to drag or air resistance will be equal and opposite his weight force. In other words, the net force would be 0. Right? If we added up these two arrows, just put them side by side, they would cancel each other out. So the net force would be 0. So the acceleration would be 0, which means he's traveling at a constant speed. So that's in section C. He's at terminal velocity, no net force, drag is equal to weight force. However, in section A, we said he was accelerating. So to accelerate, the net force can't be equal to 0, right? If it was, he'd be at a constant speed. So therefore, acceleration, is non-zero. He is accelerating. And he's accelerating downwards. So the net force will actually be acting downwards. Meaning the upwards force has to be less than the weight force. Because when we add these two arrows together, notice the weight force is a little bit longer, which means the net force is acting downwards by that difference. And so answering this question, all as we need is the arrows and their relative sizes. However, doing this little argument about the net force and accelerating will help us a lot in the next question. All right, and do make sure you draw your arrows, with a ruler, unlike me. And if they are equal, putting a dash like that clearly shows that you're trying to convey that they are equal, instead of relying on your drawing skills, which could be great or might not be. In part 2, all right, now this is just explaining what we drew. So explaining what we drew. So we gave some bullet points already. Let's put it into a few sentences. So if you haven't tried this already, try it now with these points in mind, and then come back to this. So comparing vertical forces, so in section A, the weight force is greater than the drag force. This results in unbalanced forces where the net force is acting downwards this causes Felix to accelerate downwards. And of course, that's by Newton's second law, where the net force equals mass times acceleration. All right. Whereas in section B, the weight force is equal to the drag force. This results in balanced forces, balance meaning they're equal and opposite. And then this means Felix is either stationary or traveling at a constant speed. But we can just say, from this context, is traveling at a constant speed. And we actually know from the speed time graph that that was 350 meters per second, but we don't need to mention that here because we're just explaining the motion, linking it to the vertical forces. So just to summarize this one, in section A, our weight force is greater than drag, meaning we have unbalanced forces, so the net force is acting downwards. A little thing we could actually put in here is that the net force is non-zero. And then that results in him having an acceleration downwards. Whereas in section B, since the forces are equal, the net force was 0, meaning he's traveling at a constant speed, or stationary, but we could just say that there's no change in speed or it's a constant speed. And then Felix will keep falling and then open his parachute and then land safely. Alrighty. Well, I'm going to go have my second cup of coffee. Have a good day.